Hello everyone, welcome to the last lesson of ordinary differential equation of this segment, and in this lesson we are going to learn about the boundary value problems. So if you remember, in the last few lessons we have covered the Runge-Kutta methods like the Euler's method, Hans method, midpoint method, or first to fifth order Runge-Kutta method. So in all of those cases, those methods are actually applicable to simple first order ordinary differential equations. But what will happen if the order of the differential equation increases? Let's say a second order differential equation. In that case, the methods that we have learned will not work out for those cases. As a result, we need some special methods for handling higher order differential equations. The methods that we learned, those were for only first order differential equations, but for higher order equations, higher order differential equations, we need some other techniques. So in the first, the number of conditions that we need to use for a ordinary differential equations is equal to the order of the differential equations. That means, let's say if I have a first order differential equation, then I will need a single condition to solve the differential equation. So if you remember in the previous lessons, when you used the Euler's method or Hans or Runge-Kutta methods, we used a single condition. That means we were given the initial values at the data point, at the initial data point. So that was the single condition that we were given. Because it was a simple ordinary differential equation, the order was 1. That's why we needed a single condition, and we were given the initial problem. So those were the initial value problems, because we are given the initial value of the function at the initial data point. Okay. Similarly, let's say I have a second order differential equation or third order or higher order differential equations. If I have the conditions, the number of conditions will depend on the order of the differential equations. If all the conditions are given at the initial boundary of the data point, let's say in this case I have two differential equations, dy1 by dt and dy2 by dt, and I have the initial conditions at t equal to 0. That means that at the initial point I have both of these conditions. That means it's an initial condition problem or initial value problem. Okay. So similarly, if all the boundary conditions, what I can say, if all the conditions that are needed to solve the ordinary differential equations are given at a single initial point, then that problem is called an initial value problem. Okay. Now let's move on to another problem, which is known as the boundary value problem. Okay. Why this is called the boundary value problem? Because all the conditions are not given at the single point. That's why it is called the boundary value problem, because the conditions are given at two ends of the data point space. Let's say this is a function and I have given the ordinary differential equation, which is a second order differential equation. Since it is a second order differential equation, I need at least two conditions to solve these equations. Let's say I am given the two conditions at x equal to 0, that means at the initial boundary, and at x equal to L, that means at the end boundary. So I am given the conditions at the boundary points, and that's why it is called a boundary value problem. Okay. The previous one was the initial value problem, because all the conditions were given at the initial point, but right now I am given the conditions at the two boundaries or the boundaries, and that's why it is called the boundary value problem. Okay. So I guess you already understand the details, the difference between the initial value problem and the boundary value problem. So the initial value problems or the boundary value problems, if the order of the differential equation is higher and it is a boundary value problem, in that case I cannot use the techniques that I have learned so far. That means I cannot use the Runge-Kutta methods or the Hans method or the midpoints method. Those methods cannot be used directly at these boundary value problems. Okay. So I need some special techniques to solve these problems. So some of the techniques that are frequently used for solving such boundary value problems are the shooting methods and the finite difference method. So the shooting method is very straightforward. The shooting method is actually based on the converting the boundary value problem into an equivalent initial value problem. Okay, so that initial value problem, that in case of converting these boundary value problem, I have to go through the trial and error approach. Okay, so first of all, I am going to estimate some of the results using the initial value problem, and then I am going to find out the error based on the approximated results. So if the error is above a certain limit, then I reapproximate the results using a different initial condition. As a result, it's an trial and error approach. This shooting method is actually a trial and error approach, so that is not very efficient actually. So that's why we are going to use the finite difference method. You already know the finite difference formulas that we have covered so far in the lesson 4, and we will see that whenever we are just substituting the differential term in a differential equation using those finite difference formulas, then those differential equations will be converted to a simple algebraic equations. Okay, so that's why this finite difference method is so frequently used. That's because it is so easy to understand. Okay, so let's look at an example. Let's say I have a thin rod which is situated here. So the initial boundary is at x equal to 0, where the temperature is T1, and the end boundary is at x equal to L, where the temperature is T2. Okay, and I have to find out the temperature along this rod. Okay, so that's our target. I need to find the temperature at different points along this rod. So the differential equation that is used to characterize the temperature flow along this rod is something like this. So it's a second order differential equation. Okay, H prime, in this equation H prime is denoted as the heat transfer coefficient, which has a unit of per meter square, and the term Ta, it is denoted as the dissipation of the temperature in the surrounding environment. Okay, so Ta means the temperature distribution, the temperature dissipation in the air. That means I am assuming that around the this thin rod there is air, the medium is air, the environment is air. That's why we are using the notation Ta. Okay, so its unit is in degrees centigrade given. So we are given the parameters. The rod is 10 meter long, that means L equal to 10 meter. The heat transfer coefficient H prime is given as 0.01 per meter square, and the heat dissipation is given as 20 degrees centigrade. So the boundary conditions are given as T of 0, that means at x equal to 0 the temperature is given as T1, which is 40 degrees centigrade, and at the end of the boundary we are given the another temperature, which is the T of 10, which is 200 degrees centigrade. So these are the boundary conditions and these are the parameters. So I need to find out the temperature at different points along this rod. So that is the problem. Okay, so I am going to use finite difference approximation. If you remember the difference approximation of second order difference approximation from lesson 4, you will see that the difference approximation can be represented something like this. Okay, so if you do not remember this equation, please go through the details of lesson 4. Okay, so once we know the differential equation and differential term here, we can substitute this term into the original given equation, ordinary differential equation. Then the equation will look something like this. Okay, so this is the heat transfer equation after we have substituted the term d square by dx square by the difference, first finite divided difference formula. Okay, so look at this. We have the Ti term here, the temperature Ti, and here we have the temperature Ti. That means if we just collect the similar terms and just manipulate this whole equation, we will get an equation that looks something like this. Okay, look at this, we have the temperature at nodes Ti minus 1, Ti, Ti plus 1. So that means this is a general differential difference form of the original heat transfer equation. So we have just substituted the differential term with the finite divided difference formula and then just algebraically manipulate to get this algebraic equation. So this was the we were given the original differential equation, and we have just converted that differential equation into a simple algebraic format. So we can just use this algebraic format for our purpose. So now we have just achieved the simple algebraic format of our original second order differential equations. Let's now use this equation 1. Okay, so we are given the whole rod. Let's say I want to find out the temperature at these two nodes. Okay, so these two nodes are situated along the rod, or we can find out the temperature at these four nodes. So initially I have to define the number of nodes there where I want to find out the temperature. Okay, so there are infinite number of possible points along this road, so I cannot just use infinite number of data points. So I need to first define the number of data points, the number of nodes where I want to find out the temperature. Okay, let's say I want to find out the temperature at these four nodes, and these four nodes are equidistant to each other. So that means the whole rod is 10 meter long. That means the first node, this first node is situated at x equal to 2, the second node is situated at x equal to 4, the third node at x equal to 6, the fourth node at x equal to 8, and then the x equal to 10, the final boundary. So these four data points are equidistant along the original rod. So I want to find out the temperature at these nodes. So what I am going to do, I want to apply equation 1, the difference equation that I have derived from the original second order differential equation at these four different nodes individually. Okay, let's say I want to apply equation 1 at this first node. So at this first node the temperature is T1, at the second node the temperature is T2, similarly T3 and T4 are defined. So if I apply equation 1 at this first node, then the algebraic equation will look something like this. So this is the equation that I have that is being achieved by applying equation 1 at x equal to 2 meter, that means at this node. Okay, so this is the temperature equation that I have derived at this node. So look at this, at this equation I have, in this equation I have T1 and T2, both T1 and T2 are present in this equation. Similarly I want to apply equation 1 at the second node. Okay, so if I apply equation 1 at this second node, that means at x equal to 4 meter, then the equation will look like this. Okay, this is equation 3. Similarly equation 1 is applied at node 3 and at node 4, and we will get similarly two different other equations. So that means at 4 different nodes I will achieve 4 different difference equation. Okay, equation 2, equation 3, equation 4 and equation 5. Okay, so equation 1 was the original difference equation, then I applied the difference equation at these 4 different nodes and I have achieved 4 different equations. So if I just summarize these 4 different equations into a matrix format, you will see that this is the coefficient matrix. These are the unknown terms, that means T1, T2, T3, T4. These are the 4 nodes that I want to determine the temperature, and these are the constant terms. So if you just note carefully, this is a system of 4 equations. It can be solved using Gaussian elimination, Gauss-Seidel method, Jacobi method, complete Gaussian elimination. Those methods can be easily applied for solving such system of equation, but there's an special interesting thing is here, that this is a tri-diagonal system. So if you just notice carefully, only the tri-diagonal elements are non-zero. That means it's a tri-diagonal system. So a special method that is being used for solving such systems, if you just remember, that is the Thomas algorithm. This Thomas algorithm was specially designed for handling such tri-diagonal system. So you can use the Thomas algorithm for solving this system. So if you just solve this system, you will just get the values of T1, T2, T3 and T4 to be something like this. So these are the temperatures that are being calculated for the nodes of T1, T2, T3 and T4. Okay, so I have just used 4 different data points. You can use a more number of data points here. So the number of data points will define the number of equations that you will have. So if you use more number of data points, you will have a larger system of equation. Okay, so that's how you calculate the temperature along the rod. That means the original differential equation was a second order or ordinary differential equation, and it was a non-differential equation of temperature. Now we have solved that second order equation by using finite difference method to find out the temperature along the rod. Okay, so that's what is actually the solving differential equation is, because we are just finding out the dependent variable at different data points. Okay, so now let's find out another special concept here. We have just used fixed boundary conditions. That means we are given the temperature at these two fixed boundaries. We are just given the fixed boundary conditions. That means T1 was 40 and T2 was 200. Those are fixed. That's why it is called the fixed boundary condition, or another name is Dirichlet boundary conditions. But sometimes the fixed boundary conditions are not given. Rather, we are given the derivative of a boundary. That, let's say at the boundary x equal to L, we are given a fixed temperature TB, but at the initial boundary, that means at x equal to 0, we are given the derivative of that boundary condition. We are given the derivative of the temperature. So this is not the fixed boundary condition, rather it is a temperature which is a differential term of the temperature. That's why it is called a changing boundary condition, or its another name is Newman boundary conditions. Okay, so the previous one was Dirichlet boundary conditions, but now we have the Newman boundary conditions. But the problem is here that for Dirichlet boundary conditions, we applied equation 1 at the inner boundary, at the inner data points. Okay, so at the inner nodes that we have just defined. So in case of Dirichlet boundary condition, we just apply equation 1 at these internal nodes. But in case of Newman boundary condition, we apply equation 1 not only at the internal data points but also at the changing boundary. Okay, so let's look at the example that we will be showing in the next slide. So let's say this is the original difference equation, that means the equation 1. Okay, so we are just applying that equation 1 into the Newman boundary. That means at the changing boundary. The changing boundary is at x equal to 0. So we just apply the Newman, we just apply equation 1 at this boundary too. So in the previous case, we are just given the Dirichlet boundary condition, and that's why we did not use the equation 1 at the boundary points. But now we are given the Newman boundary conditions, that means the changing boundary conditions, and that's why we need to use equation 1 also at the changing boundary, that means at x equal to 0. So if we use the equation 1 at x equal to 0, you will find out this equation 6, and if you notice carefully that we have a term which is t minus 1. So this is not normal. T minus 1 is beyond the boundary. Okay, so how can we just determine this t minus 1? So if you just remember, we can use the central divided difference formula from lesson 4. If you remember, the central divided difference formula can be denoted something like this. So this is the differential term at the initial boundary, that means the changing boundary, at the changing boundary condition, and at that boundary we can easily apply the central divided difference formula, which looks something like this. So you can easily manipulate this formula to get the value of t minus 1. So t minus 1, to calculate t minus 1 you need to know these values. So t1 is already given. I mean the t1 is an internal node, so I can easily calculate those by solving the system of equations. And dt by dx at x equal to 0, this is the boundary condition, changing boundary condition that is given in the question. So I know all the terms on the right hand side, so I can easily calculate this t minus 1, right? So once we know the t minus 1, we can easily substitute these equation, that means substituting equation 7 into equation 6, we will get a new equation which looks something like this. So this term dt by dx at x equal to 0, we already know this term because this is the boundary condition that is given in the question. Okay, so the summary is that in case of Dirichlet boundary condition, you apply equation 6 at all the interior nodes, or you can say we apply equation 1 at all the interior nodes. But in case of Newman boundary conditions, we apply equation 1 at all the interior nodes. Also we apply equation 8, that means this equation, at the derivative boundary, that means the changing boundary. Okay, so that's the difference between the Dirichlet boundary condition and the Newman boundary condition. So please be careful whenever you are using whenever you are solving a boundary problem, whether the Dirichlet conditions are given or the Newman conditions are given. You have to be careful about that. Okay. So after applying the difference formula at whether it is the Dirichlet boundary conditions or Newman boundary condition, we will have a system of equation. We can easily solve the system of equation by proper solution technique like Thomas algorithm, Gaussian elimination, Gauss-Seidel methods, and something like those. And once we solve those problems, solve the system of equation, we will get the temperature or the dependent variable at the specific data points. Okay, that's how we solve a boundary value problem. So another kind of problem we have covered so far, the initial value problem and the boundary value problem. Another kind of problem that frequently occurs in engineering practice is eigenvalue problem. So such kind of problem appear mostly in problems involving vibrations or elasticity or oscillating systems. So one example is that you will encounter eigenvalue problem in quantum mechanics whenever you are solving a Schrodinger equation. So in solving a Schrodinger equation, you will find out that that problem is actually an eigenvalue problems. Okay, so that is one example of eigenvalue problems. So eigenvalue problems are special kind of numerical problems. To solve an eigenvalue problem, we can apply the finite difference method, no problem in that. But we can also apply other methods like polynomial method, power method, Jacobi method, Givens method, and also the Householder's method, Euler method, Currer method. There are lots of methods for solving the eigenvalue problem. Okay, so I would suggest you to go through such special kind of problems. You can go through the details of the sections in Stevenson's book. So if you want to find out how to solve an eigenvalue problem, you can go through details of the book. So I am not covering the details of the eigenvalue problem. So please go through the details from the Stevenson's book, and I can assure you that you can easily understand the application of finite difference method in solving the eigenvalue problem. But to find out these methods like from 1 to 7, the polynomials to QR methods, to find out these special methods, you have to go through some advanced textbooks and the literature. Okay, so that's up to you. So in this lesson I have covered the basic difference between the initial value problems and the boundary value problems, and I have shown you the difference between the Dirichlet and the Newman boundary conditions, how those boundary conditions actually affect the system of equations. Okay, so I have also shown you a physical problem, that means the temperature distribution along the road, that how that physical problem can be approached from the perspective of finite difference formulas by using both Dirichlet and Newman boundary conditions. Okay, so please try out the MATLAB code that I have attached with this video mentioning the finite difference method for solving a boundary value problem. So please go through the details of that code so you can, so that you can understand the application of finite difference method in solving such boundary value problems. Okay, so through this lesson I have actually covered at least the basics of the solving techniques for ordinary differential equations. So I guess this lesson ends the discussion of solving ordinary differential equation. In the next section we will start learning about solving partial differential equations. So this section was all about ordinary differential equations, and in the next section we will see about the details of partial differential equation solving techniques. Okay, so till then, thank you so much.